All right, so question number 4. Compute the 90% confidence interval for the proportion of heads observed if we flip a coin 100 times and observe 65 heads shown up. So here, just analyzing the problem itself, we're given a confidence interval. This 90% is our confidence level. And it's telling us that we're working with proportion. So immediately do not look at the problems that are going to have the mean included in them, because we're not going to be given that. Okay? And here we're given a trial where we flip coins. And we had it 100 times. So if we did that trial 100 times, this is going to be our sample size. And then observing is sort of telling us what the successes are, because that's what we're caring about. That's what we're looking for. And 65 heads. So this is going to be more like our characteristic for that proportion. Okay, so we're talking a lot about proportions here. To compute this, we look at the equation for the confidence interval for the C distribution, and we see that we need p hat, q hat, the z critical value, and the sample size. So we know that the sample size already is 100, so we can fill that one in immediately. We know that the equation for p hat is going to be r over n, where r is the number of successes that we have and n is the sample size. So we are going to do 65 over 100 here and get 0.65. We know that q hat is the complement of p hat. So this is going to be 1 minus 0.65, and that should give you 0.35. And finally, we want to look at our z critical value. Specifically, we know that the critical the level of confidence is 0.90. So I'm going to rewrite that in our little bucket of numbers on the side here. And I'm going to find the number that corresponds at 90, which we know is 1.645 based off of this chart that is given to us in the formula book. Okay, so now that we have all of our variables, we can plug them into this confidence interval equation into our calculator and compute the answer. So p hat is equivalent, or plus or minus the margin of error, which is our critical value, z critical value, multiplied by the square root of p hat q hat over the sample size. Okay, next we're going to plug in all of the numbers. So p hat is 0.65. So everywhere we see p hat, wherever we see the p hat, we're going to put 0.65. The critical value is 1.645. Then we're going to take the square root of p hat again, which is 0.65. Q hat, which we calculated as 0.35, and we're multiplying those two numbers together. And then we're going to divide by our sample size, n, which is 100. Okay. So, plugging this into the calculator, I want to simplify everything underneath that square root first. So I'm going to take the two numbers in the numerator, 0.65, and multiply by 0.35, multiply them by each other, which gives me 0.2275. If I divide that number by 100, I end up with something that looks like this. So I'm just going to rewrite everything. 0.002275. Okay, So that number in the square root is the value of the fraction. I'm going to take the square root of that number, and we get 0.65 plus or minus 1.645 times 0.047. It's like 696960071, but I'm going to round to the nearest 10,000ths, and that's going to give me that's going to give me a 7 there. Okay. Multiplying 1.645 and that long decimal to each other, we get 0.0785. And then to create the margin of error, we subtract to get the lower boundary and add to get the upper boundary. So we have 0.65 minus 0.0785. That should give us 0.5715. And then we have 0.65 plus 0.0785. Which should give us 0.7285. So this is our confidence interval for the problem. The step above is the calculations for finding the boundaries based off of the equation that we have on the top here. Okay. So I think the biggest problem that you can come across with this is not knowing where to start with the formula and identifying the correct variables. So variables here are super important. And then from there, it's plugging it into the formula and getting your final answer. Okay. Question 9. If we want to have a 90% confidence interval about the mean and have a margin of error of 2, what will the minimum sample size required be if the population standard deviation is 5? Okay, so here, buzzwords that it gave us mean, so we can eliminate any equation that has proportion in it. And they want the minimum sample size. So wonderfully, we have an equation that's literally called a minimum sample size mean. So that would probably be a good place to start here. So copied over, that is our equation here. And we can start listing out what variables we have. So we have, to find the critical value, we have to know what our population standard deviation is, and we need to know what the margin of error is going to be written out as. We don't know what n is, that's what we're finding. Okay, so this is the same as 0.90, which if we look on the previous table, I didn't really copy it down again. It's 1.645. The population standard deviation is given to us clearly in this statement of 5, as 5. And the margin of error is given to us in this statement as 2. Oops. Let me keep everything as a uniform. There we go. Okay, and now we plug into the equation. So rewriting the equation, we have n is equivalent to, in parentheses, the z critical multiplied by the population standard deviation divided by the margin of error e squared. The z critical value is 1.645. So we're going to plug that in there. The population standard deviation is 5, so we're going to plug that into the numerator as well. And the margin of error is 2, which we're going to plug in as e in the denominator. So plugging all these variables in, we have 1.645 multiplied by 5 all over 2. And all of this is squared. So just to keep the color coding together, that is how we plugged it into the equation. Okay, doing this math into our calculator, we have 1.645 multiplied by 5. That gives us 8.225. We're going to divide that by 2. Of course, everything is squared still. I'm going to reduce this fraction by dividing by 2. And that should give us 4.1125. And of course, that number is going to be squared. When we square that number, we get 16.91. Okay? With sample means, you're always going to want to round up. So always round up. But thankfully for this problem, based off of before I go into that topic, it's specifically to the nearest whole number. Because again, when we're talking about sample sizes, we can't have a portion of a person. We need to have the whole person in the study, for example. So it doesn't really make sense for us to have any kind of decimal. So we want to make sure that we're using a whole number here. Thankfully for this equation, we are given, it's already telling us to round up based off of the tens digit, but always make sure that you want to round up, even if it said 16.21 instead, for example. So that means that our sample size, the minimum sample size that we're going to want, is going to be 17 here. Okay. Okay. Number 11, what does the confidence interval tell us, and what does the confidence interval not tell us? So here, a confidence interval gives us a plausible range of values for the population parameter to be. And at the confidence level, it tells us how confident we are that the true value of the population parameter falls within the boundaries of the confidence interval. Okay? So it's basically giving us a confidence of the true value. And if the samples were created within this population, approximately 95% would be in this range. This is assuming that the critical value is 0.95 here. Okay, just to give a bit more context for that. And what it does not tell us is that the probability of the true value of the mean falling between the boundary is equal to the confidence interval. So here, you want to disassociate probability with confidence interval. But what's higher yield for your exam here is going to be these 2 points. And then you're also going to want to make sure that you remember that it's not a probability question when we're talking about the confidence interval. Okay. And that is the end of Module 4.